Hello and welcome to session 1 of Climate Geoengineering GeoE Live. My name is Will Burns and I'm co-executive director of the Forum for Climate Engineering Assessment at the School of International Service at American University. And I'm here today on the campus of Stanford University with Dr. Katharine Mach, who is a senior research scientist here at Stanford, as well as the director of the Stanford Environment Assessment Facility, which directed the science for the last sessions of the Intergovernmental Panel on Climate Change. At the outset, I want to remind everybody that you can be part of the conversation through tweeting at the hashtag GeoELive. And then what we want to do in this session is a couple of things. First of all, I want to set the table and talk about what geoengineering is for those who have not spent a lot of time in this field. Talk about the broad categories of geoengineering, which will be discussed in detail throughout the course of the rest of the day. And then I'd like to discuss with Dr. Mach one specific category of geoengineering, which is carbon dioxide removal options, and more generally, why we've moved from what even a decade ago was largely in the realm of theoretical in terms of climate geoengineering to looking at this in earnest in terms of policymakers and scientists. So at the outset, a very broad definition of climate geoengineering is large-scale technological interventions that are used to combat the impacts or the phenomena of climate change. And when we talk about climate geoengineering, we generally look at two broad categories of how we might intervene to address the climate issue. The first of these categories is solar radiation management approaches. And these are approaches that seek to reduce the amount of incoming solar radiation into the atmosphere. These include things like scattering sulfur dioxide into the stratosphere to scatter sunlight away, brightening clouds, or in its most exotic form, launching mirrors on geosynchronously in space to reflect sunlight away, to exert a cooling impact. The second broad category is carbon dioxide removal options. And these are approaches that seek to reduce the amount of carbon dioxide in the atmosphere. And by doing so, reduce the amount of trapping of the greenhouse gases that exert a warming impact. And with that in mind, what we want to do now is look at how we got to where we are and what carbon dioxide removal approaches may provide in terms of benefits, potential risks, and what our research agenda should look like in the future. So I'll turn to our first question, Dr. Mach, and that is climate geoengineering. As I said, even a decade ago, this was largely in the realm of fantasy for many. But now there's a lot of discussion of this in the Intergovernmental Panel on Climate Change reports, in various government research programs, etc. Why are we thinking about intervening in the environment?
So the backdrop for climate engineering in many ways is our current moment in the climate challenge. So if we think about our emissions of heat-trapping gases to date, what we know is that we already see widespread impacts, consequential impacts on every continent, and we can even look at individual extreme events like a drought or a flood and see the ways that we're driving up the risks. Second key underpinning factor is that we know that increasing magnitudes of warming drive up those risks, especially if we persist with continued high emissions. That said, the planet as a whole is making a lot of progress in responding to climate change. Our emissions of heat-trapping gases globally have slowed down in terms of their increases through time. We're also seeing vast acceleration in terms of our deployment of clean energy solutions. But when we think about kind of some of the goals on the table of what it means to keep people safe in a changing climate, we can think about something like the long-term goal in the Paris Agreement, which is limiting warming to well below 2 degrees Celsius. So that ambitious goal, necessary to really keep people and economies vibrant and resilient in a changing climate, has some key features that become really important when we think about what we do next and why geoengineering is important to have on the table in a variety of different ways. And so I think a little physics lesson could be super helpful here. So in terms of our emissions of carbon dioxide into the atmosphere, the warming from CO2 that we put into the atmosphere is nearly permanent. So any goal we set, like keeping warming to 2 degrees Celsius or below, has a carbon budget associated with it. And so for a good chance of keeping warming to 2 degrees Celsius, that budget is 3 trillion tons of carbon dioxide. Once we've emitted that much, we have a good chance of having warmed the planet by 2 degrees Celsius. Now, in terms of the near-term urgency, the hard reality is that the carbon budget math is intense. We've already put 2 trillion tons of emissions into the atmosphere. At 2 decades more of our current global emissions, we will have fulfilled the budget for 2 degrees Celsius warming. And so that's really where things like carbon removal come into the picture. They can effectively expand the remaining carbon budget, giving us more ability to ambitiously rein in our emissions of gases through time and limit dangerous climate change. In terms of the end game energy system, what it will take to solve the climate challenge, this is a global transformation of how we use energy, how we use land. And what we know is that things like carbon removal can give us some flexibility. There are things like long distance transport or airplane emissions or how we make cement and steel that are really hard to decarbonize fully. And that's where things like carbon removal can come in. Carbon removal can also give us some flexibility in terms of shaving off the peak of how much the globe warms or enabling overshoot. And finally, I'd say that there are actually some compelling
Could you explain
benefits.
overshoot for the audience?
Great. So the basic idea is that once we put carbon dioxide into the atmosphere, we've got near permanent warming. But if we pull carbon dioxide out of the atmosphere, we can basically cool down the planet through time. I know a little bit later we'll talk about some of the risks, and there's some really important uncertainties about these peak and decline scenarios, but it's basically enabling global temperatures to go up and then to come back down.
Okay, great. All right, well, with that in mind then, what are some of the options that we're looking at in terms of carbon dioxide removal, and what would be their benefits, and over what time frame would this occur?
The spectrum of carbon removal, I think, can be easily laid out, running from biology to engineering in terms of how we're getting carbon out of the atmosphere. So I like to think about that spectrum as having really 3 buckets. So the first bucket is things really tied to ecosystem and agricultural stewardship. So for example, when plants grow, like this tree here, it's through photosynthesis, taking carbon dioxide from the atmosphere and fixing that into the plant matter, the stuff of life. And when forests grow, when we plant trees, when we change how we manage forests, so for example, logging less frequently, when we change our agricultural practices such that more carbon goes into the soil, we're changing how much carbon is stored in the land. And oftentimes that is something that is relatively low cost, that is really tied with lots of benefits for biodiversity or water quality or recreation. Although there are important questions about how vast that scope could be, what the total amount of carbon increase could be, and especially what it could be if we are in a scenario of large amounts of climate change where there's risk of loss of that carbon. That's bucket number 1, stewardship. Bucket number 2 is still relying on biology to get carbon out of the atmosphere, but there's more engineering. So in particular, as you mentioned in the IPCC in the last round report, there was a lot of attention to something called bioenergy paired with carbon capture and storage. So again, you're using plants to store carbon dioxide from the atmosphere, whether that's into a tree or something that's more like a bioenergy crop. And then you're using that plant matter to either generate biofuels or electricity. But as you do that, when the plant now combusts and it releases its carbon dioxide into the atmosphere, or you're fermenting ethanol and you get a pure stream off, you're capturing that CO2, compressing it, and injecting it underground where it can be stored nearly permanently in geological structures. The third bucket is fully engineered. So things like direct air capture, where for example you're relying now on chemistry, human-produced chemistry, to get carbon dioxide out of the atmosphere, and again compressing it and injecting it underground.
Right. And how do you capture carbon dioxide from the atmosphere using direct air capture?
I think an interesting aspect is when we think about carbon dioxide in the atmosphere and why it's hard to catch, so to speak, it's at 400 parts per million about. So that's kind of 0.04%. It's very low concentration. And so either through temperature-based approaches or basically chemistry, where you're using molecules that can grab that CO2 and then release it in your chemical reaction process. You're taking CO2 that's an incredibly low concentration, grabbing onto it with chemical molecules that we have industrially produced, and then using that to release that CO2 and use that to inject underground. So the key contrast there is, are you relying on a plant through photosynthesis to get the CO2 out of the atmosphere, or is it more chemical?
Great. Okay, so we've now outlined what some of the possible carbon dioxide options are. What would be the promise of these? How much could they reduce atmospheric concentrations of carbon dioxide, and over what kind of time frames? Is this something that's going to happen a couple weeks after we deploy these things, or is it a much longer process?
So a really important backdrop for this is thinking about what have some of the assumptions been? What does it mean to kind of right-size our expectation for carbon removal, and where has the broad dialogue been scientifically and in society? And so in some ways the important backdrop is that as we've used economic models, stylized models, to think about how the globe might reach 2 degrees Celsius by the end of the century, in some of those models there have been vast assumed deployments. So basically starting from 2020, just a few years from now, ramping up bioenergy crops at much faster rates than anything we've ever accomplished with agriculture, such that in the second half of the 21st century we could be pushing towards many billion tons of CO2 being removed from the atmosphere each year. I think the key thing is that that might be something that works well in a very stylized, back-of-the-envelope type thinking on possible trajectories. But we know that by contrast, where we've done carbon dioxide removal to date, for example, capturing CO2 coming off of an ethanol biorefinery plant in Illinois, that's 1 million tons of CO2 that we've been injecting underground per year. So 1 million tons is super different than many billions of tons at the global scale. Something like California's Forest Offset Program has been doing really rigorous work in terms of changing logging practices for projects participating in the program, and the magnitude there has been 5 million tons per year. So in some ways this question of how much, how fast has to grapple with the fact that we have some really big open questions in terms of how rapidly we can scale approaches that are working really well at the million-ton scale right now, and how big they could potentially go. And we can talk maybe a little bit later about how we've been driving that through some research here at Stanford.
Great, thank you very much. Okay, so with that in mind, what are some of the risks? Virtually any technological intervention at this scale, right, must have some risks. And what are some of the things that we need to be looking at as we decide as a society if we should be deploying these technologies and deploying them at a large scale?
So I think a first key point is that we have clear understanding that carbon removal may be a very important part of how we address the climate challenge. It has some huge benefits, as we discussed, in terms of the hard to decarbonize emissions and giving us flexibility through time. But the risks really come into focus if, in particular, we assume that this is an easy, quick fix. It sounds like a solution in that we're just addressing the root of the problem, pulling carbon dioxide out of the atmosphere. But there are some reasons why that may not be quite as easy as it sounds in concept. So first of all, there's some real questions about the feasibility of scaling, what we were just discussing, kind of how fast and how big might we be able to go, and that it's important not to just flippantly assume that this will be something that's at the order of magnitude of a quarter of the emissions that we currently put into the atmosphere easily coming out. A second question in the risk space is really, how do we understand some of the ultimate limits for our use of carbon removal technologies? So in particular, a lot of the approaches that rely on biology to get carbon dioxide out of the atmosphere, whether that's forests or bioenergy crops, have very big footprints in terms of how much land is required. Plants are not perfectly efficient, compared to what might happen if we really ramp up our ability to capture energy through other means like solar panels. The water intensity can also be quite high. So if we take some of those vast planetary scale deployments in the 2 degrees Celsius scenarios we've seen to date, the land footprint can be up to 80% of land currently under crop production, or up to 8% of the land surface. So the risks there essentially come into focus if we assume that some of these ultimate limits in terms of land, water, or even energy requirements in the direct air capture circumstance are not going to have a role in thinking about trade-offs of our choices between food, water, biodiversity, for example. A third category of risk is going back to that concept of peak and decline. So as scientists around the globe have been evaluating the impacts of climate change for decades, they've been thinking about, well, what might happen to our ability to grow crops around the globe under different scenarios, or how might plants and animals move where they live, change when they migrate. We haven't really done much evaluation, though, of what happens when you drop emissions back down. So for example, we know there are irreversibilities in the climate system. So irreversibilities in terms of collapse of the giant ice sheets on Earth, in particular the risk associated with losing the West Antarctic in substantial part. And those types of irreversibilities might be triggered by the peak and not remedied by the decline. We also might get off-gassing of carbon dioxide and methane from permafrost that's hard to dial back even as we decline the temperature. And the final thing I'll mention is that there's something that I would call can-kicking ethics. So if those of us in the current moment in time say, easy, we could double the remaining carbon dioxide budget for limiting warming to 2 degrees Celsius, and that means we can kind of push this challenge to future generations. If vast deployments of carbon removal don't materialize, those future generations will have fewer options in terms of how they respond.
Great, thank you. Well, with that in mind, given the fact that there are some large benefits to these approaches, some potential risks, moving forward, what should a research agenda look like in this context? What are some of the specific considerations, and maybe what will it cost us in terms of research funding to do these things?
So there have been a lot of really impressive coalescings of visions of what it could take to move forward with research, development, and deployment in the carbon removal space. And that spans from a report done for the Energy Secretary that looked at what are different options that could get to the billion-ton scale, and what would it take to push them forward. The National Academies has been bringing together concepts through a report, and now another effort underway, and we increasingly see groups of scientists in interaction with policymakers and the private sector putting together pieces and how we move forward. In terms of research we've been doing here, we've really been thinking about a concept of right-sizing our expectations around carbon removal, where there are many very important ways that we should be stepping forward with options that make sense in the near term, at the same time that we not assume that these are going to be easy, big, quick fixes. So for example, in that space of stewardship, we know how to do this. It's low cost. There are many ways that should be transitioning into the policy environment of what it takes to get these projects from concept into reality, and how we grapple in terms of the research with the permanence of that CO2 being locked into trees or soil through time. We also could think about better monitoring options. It's actually really hard to know exactly how much carbon you're storing in the soil. That's a hard measurement capability, but there are ways that can be grappled with, both in terms of the policy design as well as the nature of the instruments we put out there to measure carbon dioxide. In terms of the philosophy of right-sizing in the bioenergy with carbon capture and storage space, we've been thinking about what are near-term opportunities. So for example, there are 216 biorefineries, mostly for corn ethanol in the US. Those are very low-cost opportunities to build some experience with carbon capture and storage, something that we haven't really done at big scale globally, even though the concept has been around for well over a decade. And so, for example, you could imagine tapping that pure, nearly pure stream of CO2 coming off through the fermentation process and using that to really build experience with carbon capture and storage. There are also 44% of the counties across the US that have ability to grow bioenergy crops or harvest wood, for example, that are underlied by storage basins. And so those are opportunities where, with really careful thinking about that full life cycle of impacts around biology being used for carbon, could generate experience. And then finally, in the direct air capture space, we're seeing some early experiments with really driving this from concept to very small scale to things that are chugging along year after year. I think we have a very clear understanding that the technological readiness there could be improved through really pushing forward efforts in the next decade and two.
Is Stanford directly involved in direct air capture research?
There is a little bit of work in the direct air capture space, but I would say that most of Stanford expertise has been in the space of using the land sector and also thinking about the pairing of bioenergy with carbon capture and storage.
Okay. One question that we didn't address before that's probably important for a lot of people are the costs of these options. Are these viable with the low carbon signal that we have now under Paris and certainly in the United States and moving forward? Are there sufficient economic drivers that we think these might be adopted in the future at a large scale by industry? And if not, what might we do?
So I think in terms of those three buckets we started with, the stewardship approaches, the bioenergy with carbon capture and storage, and then the direct air capture, in the present world, it's almost as if it's about an order of magnitude cost difference across those three categories. So we're kind of talking $10, $100, $1,000 per ton.
Right.
And so I think the interesting thing is the stewardship approaches are really pretty cheap. And oftentimes there are opportunities to say, around the world, there's a lot of effort in terms of conserving land for recreation, for biodiversity. And oftentimes you can think about policy opportunities that are combining those different types of financial flows for multiple goals that are totally intertwined in terms of stewardship to create that financial signal. California's forest offset program, which we discussed a little bit at the start, is basically putting offsets into the cap and trade market so that industrial emitters within the state can purchase those offset credits. We definitely don't want to rely just on cap and trade type financing mechanisms into the future, but they're low cost enough that there are a lot of near-term opportunities for getting creative in the policy landscape. In the bioenergy with carbon capture space, it is into the realm where we don't necessarily have sufficient financial signals in the current world. Although the reason why we've been thinking in particular about the ethanol CCS is that in California we've got a low carbon fuel standard. There are ways that both in Europe and the US, those opportunities are cheap enough in that category that they can tie to policy instruments we already have. And in the direct air capture, the real question is, can we drive that cost down into the future?
Great, thank you very much. I'm going to take a question from our audience. It says, any thoughts in terms of the term geotherapy versus geoengineering? My understanding would be that therapy would include more naturalistic changes.
So for the last intergovernmental panel on climate change, among many different things, I was in charge of developing the glossary. So I've thought a lot about the terminology in the climate space. And I think a key aspect is that, as you emphasized at the start, there are many different types of geoengineering. They range from planting a tree to putting mirrors into space. And that is a radical spectrum, and I think it's really important that we be careful when we use terminology that we not conflate all of those options, given that they have very different benefits, costs, risks, and trade-offs. So I think I would agree that something like therapy might apply from some value-based perspectives in a lot of different categories, but even just one blanket term for all of these different options simplifies quite substantially.
Great, thank you. Do you have any concluding thoughts at this point in terms of moving forward?
I like to think about climate change as a way to build a better world, and I think that's in some ways an easy opening in that climate change impacts affect everyone around the world in terms of their economic well-being, their health, and that means that so many of the responses to climate change can tie to those goals. And I think when we think about geoengineering, it's really important to keep our eye on the ball. What problem are we looking to solve? And when we can think about easy opportunities where these make sense in terms of responding to the direct climate signal, but also tie with what else people are trying to achieve economically in terms of jobs, in terms of the health and well-being of land and people. Those are some of the opportunities where we can say climate engineering can be a way to build a better world.
Great, thank you very much. So we've reached the end of this session. I'd like to first of all thank Dr. Mach for her perspectives in terms of climate geoengineering and more specifically carbon dioxide removal options. I'd like to thank everyone who's watched, And I'd encourage you to continue to provide your questions and your perspectives through our Twitter feed with hashtag GeoELive. And I'd like to encourage you to watch the rest of the sessions today. In a couple of minutes, there will be a live stream from American University School of International Service, which will focus on the other broad category of climate geoengineering, which is solar radiation management options. So thank you very much for watching.